In this video, we are going to discuss quantum numbers. So first, what are quantum numbers? Well, the number and distribution of electrons in an atom determine its chemical and physical properties. So it's very important to know uh, how the electrons are positioned in an atom, and that way it will help us understand some of the chemical and physical properties for that particular atom. We can describe the distribution of electrons in an atom using a set of four quantum numbers. Now, remember, according to quantum mechanics, we cannot know exactly where an electron is in an atom at any time. So we don't know exactly where the electron is, but we do know through quantum mechanics the likelihood of where an electron is to be. So we call these orbitals. So we can't tell the exact position of an electron, but we are able to determine the likelihood of the position where we're most likely to find a particular electron. And so these quantum numbers, these four quantum numbers, are assigned to each electron in an atom. So each electron has a unique set of four quantum numbers, and these four quantum numbers describe where that electron is likely to be. So its most likely position in an electron. No two electrons in the same atom can have the same set of four quantum numbers. So for example, iron, which has 26 electrons, each of the 26 electrons in iron, for example, will have a unique set of four quantum numbers. And the four quantum numbers, as we'll see, will give us information about each electron, its energy, and where it's most likely to be found at any given time. Again, although we can't tell the exact position of electron, I try to think of these quantum numbers similar to a person's address. Okay, if you tell me your state where you live, your city that you live in, the street that you live on, and the street number, then someone can find where you are, where you live. And that's analogous, not exactly, but analogous to the quantum numbers. If you know the set of four quantum numbers for a given electron, you know where it lives and therefore where it's likely to be found. So let's talk about these four quantum numbers. Again, be sure you appreciate what they're telling us. And the four quantum numbers are what are called the principal quantum number, and we abbreviate that as N. The angular momentum quantum number is L. The magnetic quantum number, M sub L. And finally, the electron spin quantum number, M sub S. So let's go through each of these and try to figure out what information each of these tells us about the likely position of an electron in an atom. So the principal quantum number, let's start with this. This is the most general one. It describes the size of an orbital and the distance from the nucleus. The principal quantum number is also referred to as the shell. Principal quantum numbers can have values of, they must be whole number integers, so you can have an n equal to 1, n equal to 2, 3, 4, 5, etc. And so a shell, as we'll see as we move on, is basically a collection of subshells. So let's talk about this in just a bit more detail. An electron may have an n equal to 1, right? Its principal quantum number could be 1. If an electron has an n equal to 1, we say it's in the first shell. So it's in the shell that's closest to the nucleus, and the closer the shell or an electron is to the nucleus, the lower the energy of that electron. So as electrons get further from the nucleus, they're located in shells that are further from the nucleus, the energy of that electron gets higher and higher. An electron with an n equal to 2, we say it's in the second shell. That's the next closest to the nucleus. So it's a little further away from the nucleus than the n equals 1 shell, and it has a slightly higher energy. So we can, if you, by knowing the principal quantum number for an electron, we can tell relatively how far it is from the nucleus and therefore how much energy it has. Is it a low energy electron close to the nucleus or a higher energy electron farther from the nucleus? Okay. So here you can see if our nucleus is down here, the n equals 1 shell, the n equals 2 shell, n equals 3 shell, they get further and further from the nucleus. Now put this in here because we're going to build on this figure as we move along. So let's take a look at our second quantum number called the angular momentum quantum number, abbreviated as L. This describes the shape of an orbital. Again, an orbital is a region of space where an electron is likely to be found. And the angular momentum quantum number is also referred to as the subshell because it's a collection of orbitals, and a collection of subshells is called a shell. A collection of orbitals is called a subshell. L values, the mathematical values for L, can be anywhere from 0 all the way up to n minus 1. And we'll show you this in just a minute in a little more detail. Each of these L values, 0 all the way up to n minus 1, are also often given a letter indication. An L of 0 is represented by S. An L equal to 1 is represented by the letter P. An L of 2 is represented by D, an L of 3 of F. And these letters give us information or tell us what shape it is. And I'll show you some pictures of these shapes in just a minute. So remember, a subshell is a group of one or more orbitals of the same type, the same energy. So let's look at these angular momentum quantum numbers in a bit more detail. Let's start with the first one. The first shell, remember atoms, they have shells, n equals 1, 2, 3, 4. Inside these shells, which are not physical things, but these shells are a collection of subshells. The first shell, n equals 1, can have an L value of 0. Remember, to calculate the L values, we take the n, our shell, minus 1. So the n equals 1 shell has an L value of 0. We said that an L of 0 tells us that we have an S-shaped orbital. So the L equals 0, that's our subshell, and that subshell contains an S-shaped orbital. An S-shaped orbital is spherical. So in other words, what we have here, pretend the nucleus of the atom is in the center. The electron is likely to be found in this region around the nucleus. What if you have an n equals 2? If you have an n equals 2, that means the electron is in the second shell. The L values for n equals 2 can be 0 up to n minus 1, so they would be 0 and 1. So the second shell has 2 L values. What does that mean physically? Well, that means we have 2 subshells, which means we have 2 different types of orbitals in the second shell. We have S orbitals and we have P orbitals in the second shell. So the first shell has only S orbitals, or an S orbital. The second shell has an S orbital and P orbitals, P-shaped orbitals. Remember, the L value gives us information about the shape of the orbitals in a particular shell. So the L value of 1 represents P orbitals, and the P orbitals are shaped kind of like this, dumbbells. And as we'll see, there are actually 3 of these, and we'll show you how we know that in just a minute. Let's move on to the another example. If you have the third shell, so electron is in the third shell, n equals 3, the L values for that principal quantum number would be L of 0, 1, and 2. So what does that mean? Again, it means that the third shell has 1, 2, 3 subshells, and those subshells contain S orbitals, P-shaped orbitals, and D-shaped orbitals. And you can see D-shaped orbitals down here. There are actually 5 of those. We'll show you that in a minute. Okay, moving on. If you have the fourth shell, so you have electron or electrons in the fourth shell. The L values in the fourth shell can be 0, 1, 2, and 3. So again, what does that mean? That means that the fourth shell contains 1, 2, 3, 4 subshells. Those subshells are comprised of S, P, D, and F shaped orbitals. And you can see the F orbitals, their shapes here. Okay, we have 1, 2, 3, 4, 5, 6, 7 F orbitals. So to kind of sum that up, the first, if you have n equals 1, the first shell, the L, you can only have one L value, which means you only have one subshell or one type of orbital in the first shell. N equals 2, the second shell, you have an L of 0 and you can have an L equal to 1. So there are two subshells or two different types of orbitals in the second shell. In the third shell, n equals 3, you can have an L of 0, 1, and 2. That tells us that there are three subshells in the third shell, and the subshells contain S, P, and D shaped orbital. In n equals 4, you can have L values of what? N equals 4, you can have L of 0, 1, 2, and 3. So you have four subshells in the n equals 4, and those subshells are S, P, D, and F. Those shapes of the orbitals in the subshells are S, P, D, and F shape. So let's look at our third quantum number. Again, we're trying to describe where the electrons are in an atom or likely to be found. The magnetic quantum number, m sub L, this describes the spatial orientation along the x, y, and z axis. These are the m sub L values are actually describe the orbitals. The m sub L values depend on the L values. Much as the L values were determined by the N, the m sub L values are determined by the L values. So an m sub L value can be negative L all the way, including 0, all the way up to positive L. I'll give you some examples of this in just a minute. And these indicate also not only the spatial orientation, but the m sub L values also tell us how many of a particular type of orbital are in a particular subshell. So let's take a look at this. If you have an n equal to 1, the first shell, we said that the L value, you only have one L value associated with the first shell, and that's a S. That's a L equals 0, which tells us that those are S-shaped orbitals. The m sub L values can be negative L up to positive L. If L is 0, then the m sub L value is 0. N equals 2. Look at the second shell. Remember we said we can have two L values, 0 and 1. That means we have two subshells in the second shell. These subshells contain S-type orbitals and P-type orbitals. The m sub L values for L equals 0 are 0. The m sub L values for L equals 1 can be positive 1, 0, and negative 1. For n equals 3, the third shell, we said we had three subshells, S-type, P-type, and D-type. The m sub L value for L equals 0, we said can only be 0. For L equals 1, it can be positive 1, 0, and negative 1. For L equals 2, we can have plus 2, plus 1, 0, negative 1, and negative 2. So what do these indicate? Well, first of all, the m sub L value tells us how many of a particular type of orbital are in a subshell. So here we have only, down here we have only one m sub L value. So there's only one s orbital in the L equals 0 subshell. Here, when L equals 1, which represents p-type orbitals, when L equals 1, we have one 2, 3, we have 3 m sub L values. That tells us that there are 3 p orbitals in this subshell. Moving up here, when L equals to 2, we have 1, 2, 3, 4, 5. We have 5 m sub L values for L equals 2. That tells us that there are 5 d orbitals in this particular subshell. So for n equals 1, for the first shell, there's one subshell, and that subshell contains only one s orbital. For the second shell, we have one s orbital, and we have 3 p orbitals in the second subshell. For the third shell, we have one s orbital, we have 3 p orbitals, and we also have 5 d orbitals. What would the m sub L values be for n equals 4? Think about that and see if you can figure it out. So remember that the m sub L values, we're told they also tell us the spatial orientation. So for example, let's look at the L of 1. We have 3 m sub L values, which tells us that we have 3 p orbitals. They also tell us that the p orbitals are located along the x, y, and z axis. So they're equal energy orbitals, but they're just located spatially either along the x, y, or z axis. Now, which is which? So this one would represent perhaps m sub L of +1. This one might be m sub L of 0, and this one might be m sub L of -1. It doesn't matter which is which, but each of these orbitals is represented by a particular m sub L value. So here are our 5 d orbitals. Okay, remember, for a d orbital, the L value is 2. So perhaps this orbital has an m sub L of -2. This one is -1. This one is 0. This one perhaps +1. And this one would be, of course, +2. Now again, which is which corresponds to which m sub L value, doesn't matter, but you do want to appreciate that each of these orbitals has its own unique m sub L value. Okay. And they tell us, of course, how many we have of a particular type and its spatial orientation. And finally, the last quantum number is the magnetic spin quantum number, m sub s. This indicates the spin of an electron, whether it spins clockwise or counterclockwise. So each orbital can hold a maximum of 2 electrons. So you may have 2 electrons in the same orbital. We have to distinguish those 2 orbitals in order to, those 2 electrons. So in order to distinguish one electron from another that are in the same orbital, we assign one of the electrons an m sub s of +1 and the other an m sub s value of -1. It doesn't matter which is which, but again, 2 electrons in the same orbital, they have opposite spins. You cannot have 2 electrons in the same orbital, according to the quantum mechanical model, that are spinning both clockwise or both counterclockwise. So each electron must be given an m sub s value to distinguish 2 electrons in the same orbital. So this table kind of sums everything up as far as your principal quantum number, angular momentum quantum number, magnetic, and the magnetic spin quantum number. You can see what the values are, or can be, and kind of what it represents. So review that a little bit, look at it, be sure you're comfortable not just calculating numerically what a quantum number value is, but understand what it tells us about an electron's position in an atom. Let's take a look at a couple of problems before we finish up. What is the maximum number of electrons that can be contained in the third shell, the n equals 3 shell? How many total electrons can fit in there? Pause the video and see if you can calculate that. Okay, so the n equals 3 shell, the third shell has 3 subshells, 0, 1, and 2. So it has s, p, and d type orbitals. There's one s orbital, there are 3 p orbitals, and there are 5 d orbitals in the third shell. Each of these can hold 2 electrons. Each orbital can hold a maximum of 2 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 total orbitals in the third shell. 9 times 2, since we have 2 electrons can fit into each orbital, would give us a maximum of 8 electrons. So the third shell would hold a maximum of 8 electrons. Okay? So maybe you want to calculate what's the maximum number that can be held in each shell. As the shells get further from the nucleus, the shells get larger, and the shells can hold more electrons because they have more orbitals. Let's look at one more problem. What are the possible m sub L values when the principal quantum number is 3 and the angular momentum quantum number is 2? Okay, pause the video and see if you can answer this one. So for n equals 3, the third shell, and the angular momentum quantum number is 2, if the angular momentum quantum number is 2, the m sub L values are going to be negative L all the way up to plus L, including 0. So the m sub L values for an L of 2 would be negative 2, negative 1, 0, positive 1, and positive 2. So these are the m sub L values. Again, be sure you appreciate what they tell us. These m sub L values tell us that the L of 2 represents what type of orbitals. L of 2 represents f orbitals, or excuse me, d orbitals. And the d orbitals, we have 1, 2, 3, 4, 5. So there are 5 different d orbitals, or 5 d orbitals in the L of 2, and they are located on different spatial orientations. So they position differently along the x, y, and z axis. So again, be very familiar with these quantum numbers, appreciate what they tell us about an electron's position in an atom, and physically what they indicate.